Hello, hello. Am I audible? Screen ಕಾಣ್ತಾ ಇದೆಯಾ? Should I start the class? Okay. Uh, Today's topic is measurements of solar radiation. In the last class, we discussed about what is meant by solar radiation, solar constants, what is beam, diffuse, and global radiation, and also solar datas with respect to the seasons, with respect to the day, with respect to the angle. We discussed the solar data. Okay, and today we are going to discuss about solar radiation, and it is very much necessity to measure this solar radiation mainly because of due to two important reasons. The first important reason is its application. uh, so nowadays we are going with more with the solar applications like a solar heater, solar cooking, and solar portable power generator we are using. So for that more and more usage and more applications, we should know how much solar radiations we are getting from sun to earth. That is the one reason. And second reason, for the perfect measurement helps to measure the efficiency. So if you know the what is the incoming solar radiation, and we can easily get the performance or efficiency of the devices. Okay, so in the daytime we get the more solar radiation. In the night and the morning time we get a less solar radiation. So based on that and at what time it is peak and what time we are getting a maximum solar radiations and what time we are getting maximum beam radiation and diffuse radiation, so those things are very much necessary. And some of the experimental determination of the energy transferred to the surface by the solar radiation required instruments which are will measure heating effect or a direct solar radiation or diffused solar radiations. And these measurements are also made by maybe the beam measurements or a diffuse measurements which responds to the solar received by the a very small portion of the solar sky. So with us, we are going to only measure a small portion, not all the solar radiations we are going to measure, only a small portion we are going to measure. And the total radiation, a type of instruments may use to measure a diffuse radiations alone by shading and sensing elements from the sun direct rays. So we either we go with a direct or we go with a diffuse. There are basic two important types of principles array devices are available to measure the solar radiation. So in the picture you are going to see there are two important type. Okay, the first one, the first important type is pyrheliometer. It's called as a pyrheliometer, and the second one is called as a pyranometer. So pyrheliometer and pyranometer, there are two important devices which are generally used to measure the solar radiation. Going to the next slide. Okay, so first we are going to discuss a so important type is a pyranometer. Okay, so this is a device, a pyranometer. It is used to, it's it is called as a pyranometer. It is used to measure direct or a beam radiation. It is used to measure direct or beam radiation. Only it is used to measure direct or beam radiation. We already know that what is meant by direct or beam radiation. Okay, the rays which are directly reaches earth crust without uh, scattering or without any absorption. Whatever the rays are reaches to the earth crust, it is called as a beam radiation, and that radiation we are going to measure with the help of this pyranometer. Okay, and here uh, in this contrast, this pyranometer, which is similar to the pyranometer, both are same. The only the difference is here we are not using any shading rings. That shading ring, which are used to reduce the diffuse radiation. Okay, they are filter the diffuse radiation. So most pyranometer used for a routine measurements operate an thermophils. We are using thermophils effect and are similar to the pyranometer in this respect. And means the operating concept is both are same, and they are different in that mechanically they must follow the sun measurement only in a direct sun rays. Only it is used to measure the direct sun rays and to avoid this diffuse component. uh, and the in practice the direct solar radiation is measured by attaching an instrument to an electrically driven uh, equipment is mounted on the on that base. It will track the sun. If the sun is move along the sky, this the whatever the mounted device is also tracking the same path of the sun. The diffuse component is avoided by installing a colorimeter, the tube and sensor to circulate, and the cone angle is approximately 5 degree. So within that 5 degree it will measure the angles, and that whatever the rays which are getting from that 5 degree, that will consider as a beam radiation or direct radiation, and that will measure by this pyranometer. And the direct solar component on the horizontal surface may also be obtained by using a shading rings. Okay, and in this done, and with the help of also shading rings, we can measure the radiations. Okay, and so whatever the uh, rays which are obtained on the shading ring, which includes both a unshaded, that is what global readings, as well as shaded, that is what beam. Okay, it will consider both. It is also another method. But in the current practice, in a solar radiometry, in the primary, there are thermo thermoelectrical transducers. We are using thermoelectrical transducers. That thermoelectrical transducers are used to measure whatever the current induced in this circuit. Okay, and however relatively a low cost, because why we are using this, because it's a low cost and photovoltaic transducers and become a more popular. And to measure the direct solar radiations, the receiving surface must be a normal to the direct rays, that is a line joining in the sun and receiver. And come to the pyranometer, there are three important types of pyranometers, and both are operating under this thermoelectric transducers. Okay, that is the base component. The first important type is Angstrom pyranometer and Abbott silver disc pyranometer and Epil pyranometer. There are three important types of pyranometers we are using to measure the diffuse or beam radiation. In the picture, you can able to see in the slide, it's a pyranometer device. Angstrom, the first important, this is what the important are, it's a commonly used device, Angstrom compensation pyranometer. It is also called as a Angstrom compensation pyranometer. So in this pyranometer, a thin blackened, a shaded magnesium strip. Okay, thin blackened magnesium strip. Okay, so here it's a black body. That is what we call it as a black body. And below that black body, there is a thermocouple and there is a stand and the halo tube and there is a protective lens. They are placed. This is and acceptance angle is 5 degree. I told the acceptance angle is 5 degree. Within that angle, it will taken as a beam or direct radiation. Apart from that angle, it will consider as a scatter or diffuse radiation. Okay, this is what the arrangement. And uh, here it is of measurement of 20 into 2 into 0.1 mm. Okay, and it's a one circuit. Okay, inside that there is a one circuit, and it is heated electrically, and that strip is heated electrically until it is at the same temperature as the similar strip which is exposed to the solar radiation. Here there are two strips. Okay, one strip is directly exposed to the solar radiation, and it is allowed to heat with the help of solar radiation. Whatever the radiations through the tube, okay, that will heat the strip. And in another side, there's a one more strip that is connected to the electric supply, so that that electric current will heat that strip. Okay, with the help of electricity, that will heat the strip. And once both the strips will attain the same temperature. Okay, so one strip is due to the solar radiation, it will heat, and another strip, it is electrically or artificially we are going to heat the strip. If once both strips are heated, that is what thermally equilibrium, okay, or under steady state, both are identical temperature, the energy used for heating is equal to the absorbed solar energy. Here, whatever the energies we use to heat that strip, which is indirectly equal to the whatever the energy from the solar radiations to heat another strip. So one strip is heated due to the solar radiation, that energy is equal to the energy is used to heat another strip, okay, electrically. That is what equal compensation. Okay, it will compensate the energy, means both energies are equal. So in this way we are going to measure the heat energy. Okay, and the thermocouple on the back of this strip, you just place the thermocouple back on the strip, and it is connected to opposite through the sensitive galvanometer. Okay, and are used for the quality of temperature, it will measure the temperature. And the energy H, and the energy H is direct radiation, and it is calculated by means of one formula, H is equal to K I square. By using this equation we can measure the energy. Okay, here simple concept, there are two strips in that arrangements. One strip is electrically heated and another strip exposed to the sun rays, so that the sun rays will fall on that strip and it will start heating. Once the temperature is both the strips are equal, then it is become a steady state, and with the help of this equation we are going to calculate the solar radiation, only beam radiation, because it will accept only 5 degree of angle. Okay, and some of the problems or some of the drawback regarding this pyranometer is, uh, the first pyranometer measurements are several folds. It should be with a several folds, and operator's angle. So operator's angle as well as several folds, and circumsolar contributions. Okay, this solar contributions, and impression in the tracking mechanism. So these are the some drawbacks of this pyranometer. The first thing is operator angle, that is what the angle. Second thing, the tracking mechanism. Okay, the efficiency of the tracking mechanism, as well as solar contributions. And of course, these are the problems we can, with the help of some alternative devices, we can easily eliminate this inability, and we can go with a high precision devices. Okay, so this is what the first important type of solar radiation measurement is, pyranometer. And next come to the second type, it is called pyranometer. So it is called a pyranometer. So this pyranometer, it is a instrument which is used to measure total or a global radiation. A global or total radiation means it is an sum of a beam radiation and diffuse radiation. But in the first type, we are going to eliminate the diffuse radiation, only we are going to measure the beam radiation. But in second pyranometer, we are going to measure both. That is what global or total radiation means. It is addition of a diffuse as well as a beam radiation. If a shading ring is attached, here we are using a one shading ring. Okay, it is attached, or the beam radiation is prevented from falling on the instrument or sensor, and then the measures only a diffuse a component of the radiations. If you don't want beam radiation, only if you want diffuse radiation, you can use the shading ring. So that shading ring will avoid the beam radiation and only it will measure the diffuse radiation. And in the most pyranometer, a sun radiation is allowed to fall on the black surface, is allowed to fall on the a black surface to which the hot junction of the thermophile are attached. Here also same, we are using the same thermophiles. In the pyranometer also we are using the same thermophiles, and pyranometer also we are using the same thermophiles. And the cold junction of the thermophiles are located in such a way that they do not receive radiation. In one side there is a cold thermophiles, a cold junction thermophiles, okay, they do not receive any type of radiation. As a result, and in another side we have placed the another thermophiles, they directly receives the solar radiation. It is a black body, okay, black body absorbs all energy and white body it won't absorbs, okay. So there is a difference. As a result, an EMF, there is a difference, and because of the difference, an EMF is proportional to the solar radiation is generated. Because in one side there is white body, it won't absorb radiation, another side is a black body, it absorbs the total radiation. So because of this difference, it will induces the EMF, okay. So that EMF is proportional to the whatever the solar radiation generated, okay. And this EMF, which is used to a range of 0 to 10 microvolts, it is of 0 to 10 microvolts, can be read and recorded for integrated over a period of time with a regular calibration. Means we have to regularly calibrate means we have to check the device efficiency regularly, and it is approximately 1 plus or minus 2 percentage can be acceptable, okay. And in pyranometer there are 4 or 5 important types of pyranometer, okay. So Apelli pyranometer, Elot solarimeters, that is what photovoltaic cell, okay, and bimetallic actionometers are there, okay, and thermo electro pyranometers. There are so many types of pyranometers are there, okay. So in that first only we will discuss Apelli pyranometer. It's a one typical pyranometers generally used for measuring a total or a global solar radiation. So in the picture or in the slide, you can able to observe this is what the device, okay. It's a pyranometer, and it is with the thermocouples on the bottom, and voltage, there is an voltage difference, okay, and a black body, above that there is a black body and protective lens and solar radiation, okay. It's a spherical lens, a protective lens. And this Apelli pyranometer, it is based on the principles as stated above. With other types also the principles is same, okay. And here also same thing what we earlier discussed, the pyranometer working, it is on the same concept. Here the difference between the temperature of black surface, which is absorb most radiation, and white surface, which reflects most solar radiation, means it won't absorb, it will only reflect. The white body reflect and black body absorb. That's why always a black color absorbs the heat, and white color it won't absorb, it will just reflect the heat, okay. By the difference of same thing, the detection of temperature difference is achieved by thermophiles. The thermophiles are placed, it will achieve the temperature difference, and it uses a concentric silver ring of 0.2 mm thick, appropriate coated a black and white, with either 10 to 50 thermocouples. We just placed 10 to 50 thermocouples junctions to detect the temperature difference. We are just used to the temperature difference between the ring. And later the modules are a wedge type arrangements, okay. There are wedge type arrangements, okay, with a alternative black and white coatings. That wedges are alternatively black and white coating, and the rings or wedges are enclosed in an hemispherical, that is a spherical protective lens, okay. And this is what the arrangements, and whatever the solar radiations are fall on that spherical rings, directly through that spherical rings it will reaches the black body, and that black body will absorbs all the radiations, okay. And there is another side is a white body, and it won't absorbs the radiations, and there is a difference in the white body and black body, it will generate the EMF, okay. That difference in the temperature generates EMF. That EMF is directly measured as or whatever the solar radiations we are getting on that black body. Okay, here there is a beam radiation is there, there is a diffuse radiation is there. Okay, it is an addition of all beam and diffuse, means it gives the total radiation. If you place the shading ring, if you place a shading ring, it will filter the whatever the beam radiation. The same device, if you use the shading ring, okay, if you use the shading ring, this is for the shading ring, okay, with the device, and this shading ring will filters whatever the beam radiation falling on that device, and it will allow only a diffuse radiation. You can measure the only diffuse radiation. And this pyranometer, if you want to eliminate the diffuse, means you have to use the shading ring. Okay, and come to the advantages of this. The temperature coefficient is extremely small. Temperature coefficient is very small and standardized to the ISO standards, as in measurements of performance ratios and performance index are accurate when compared to the pyranometer. Okay, and response time is longer compared to the PV cells. And disadvantages, it's a spectral sensitivity is impact, and so it does not absorb the complete spectrum of sun. Okay, and errors in measurements can also occur. We already know that what is meant by electromagnetic spectrum. Okay, it won't absorbs all the spectrum. And come to the applications, the solar, this type of parameters are solar intensity data can be measured, and climatological or meteorological studies, we can use these types to measure the or predict the climates. Also we can use this type of measurements. PV systems we can use for designing locations, and greenhouse can be established and expecting the requirements of installations for building structures. So these are some applications. And the last important topic is sunshine recorder. So this is the last topic in your first module. So this sunshine recorder, it's a device. It is used to measure a duration of day when there was a bright sunshine given a beam radiation. Means the duration of bright sun in a day is measured means of sunshine recorder. So the duration of bright sun in all the day, you won't get a bright sun. Only a few hours or few minutes we get a bright sun. Okay, so the duration of bright sunshine in a day measured means of sunshine recorder. Okay, so this sunshine recorders are focused by a glass sphere. That is what the construction. It's a transparent glass sphere mounted on a heavy base or a bowl. Okay, and bowl is provided below the glass sphere, and a groove is provided to a insert papers or a strip. Okay, that is a card strip below the grooves. We place the card strip below the grooves, and it is mounted concentrically with the sphere. So this is what strips, okay, strips placed, and this is a sphere, and this is a I told grooves. Below that there are a card strips, and this is tracking. Yes, this is a typical sunshine recorder device. Okay, a transparent, it's a spherical, a glass tube, a glass sphere. Okay, below that there is a grooves, and on that there is an strips, card strip. Whenever there is a light or a bright sunshine, whenever there is a bright sunshine, okay, the image is formed in a sunshine uh, intense enough to burn the spot on the card strip. So through this glass sphere, the sun rays enters, and it is concentric on the strips. Okay, and through this, though the day is the sun moves across the sky, the image moves along the strip. Thus, the burnt space below the length is proportional to the duration of the sunshine is obtained on the strip. Okay, so a spherical glass, through that the rays are enter, and it is directly concentrated on the this strip. Once that intensity of that sun rays are high enough to start burn this strip. Okay, and it is continuously burn until there is a bright sunshine. Okay, once the bright sunshine is no more, and it will stop the burning process. Okay, and the total length of burned space, whatever the total length of burned space, that will indicate the total sunshine. Okay, total sunshine in the day. It may be 10 minutes, 20 minutes, 30 minutes, or 1 hour, 2 hour. Okay, so that is what a sunshine recorder. So this is a typical sunshine recorder device. Through that glass tube, glass sphere, the rays are entered and projected on the strips. And once the intensity is high enough to start burn the strip, and it is continuous until there is a sunshine. Once the sunshine is no more, it will stop the burning process. In this way, we can measure the sunshine throughout the day. I'll show you one video with regard to the. Yes, this is a typical sunshine recorder device. You can see it's a transparent completely, and it is exposed to the sun. Through that, sun rays enters, and these are the grooves along with the strip. Just it is focusing all the sun rays into the strips, and this is an tracking mechanism. It will track the sun when the sun moves along the sky. So this is how it starts burning process on the strip, and whatever the burnt space, that burnt space length, which is equal to the sunshine, bright sunshine. If bright sunshine is more, so more burning space. Okay, so with this, I'm going to wind up the first module, complete first module.